Hi everybody, welcome back. It's Mrs. Brady. Today we're going to talk about conjugate roots. And actually by the end of this lesson and tomorrow in class you're going to practice this, you're going to be able to build a polynomial given its complex and irrational zeros. You did it before when their zeros were real numbers, and we're just going to jazz it up a little bit. It's going to have complex and irrational zeros, but you're going to be able to do it. So this is section 5.5 in your textbook, and we're going to start. We can take a look at, it's called the conjugate root theorem. It's on page 312. See, there I am. This is just like I was in class. Hey, hi Nate, how are ya? Hi Noah, hi Isaiah. Okay, conjugate root theorem says this. In a nutshell, you could read the theorem in your textbook, but what it really says is this. Irrational roots occur in conjugate pairs, and complex roots occur in conjugate pairs. So, regardless of the root, if it's irrational or complex, it comes as a pair, like peanut butter and jelly, salt and pepper, right? All right. Irrational roots. Irrational roots have the form a plus radical b and a minus radical b. They always come in this pair. The reason they're called irrational is irrational numbers are real numbers that can't be written as a simple fraction. It means they're not rational. So if we have an irrational root, it comes in a pair. The next thing we have is if we have a complex root. If we have a complex root, they're in the form a plus bi and a minus bi. Complex numbers are just numbers that have a real number along with an imaginary. You guys already learned this when we solved using the quadratic formula. So we know our answers. We always had two answers from those. Excuse me. Okay, on to the work. We have to figure out what a conjugate is first. So first we're going to look at our set of irrational numbers. Conjugates are simply this. A plus the square root of the number, a minus the square root of a number. They always come in pairs. So if I'm told that one of my answers is 2 plus radical 7, the other one is going to be 2 minus radical 7. If one of my zeros is 5 plus radical 2, the conjugate of that is 5 minus radical 2. Now this is kind of weird. If I'm told my root is radical 5, the conjugate of radical 5 is minus radical 5. All right, and now I want you to try it. You go ahead and you tell me what is the conjugate of the square root of 17. All right, did you give you long enough? Did you say it was negative 17? So when we're given one of these roots to figure out the conjugate, we just take the opposite sign. Okay. Now we're not going to look at irrational numbers. We're going to look at complex numbers. Remember, these guys have I in there. I, remember, was the square root of negative 1. It was one of your favorites. All right, just like the other numbers. The conjugate is simply the same number, but the sign in the middle is different. So if I'm given a 0 of 2 plus 3i, my conjugate is 2 minus 3i. If I'm given a 0 of 1 plus I, my conjugate is 1 minus I. If I'm given the conjugate of plus I, it's minus I. You know what example I don't have in here? What if I had 7 minus 5i? What's its conjugate? You go ahead and write it down. 7 plus 5i. So the conjugate are the same numbers, but what changes in the inside is just the sign. All right, let's put this to use. How does this work for us? Problem 1. What we're going to say is we've got a polynomial. He's a quartic. So that means he's degree 4. And if I have a polynomial with degree 4 and it has rational coefficients, I'm told if the square root of 2 and 1 plus I are roots of the polynomial, what are the two other roots? Well, I'm going to use the conjugate root theorem. And I know that if 1 plus I is a root, and if the square root of 2 is a root, I know they're conjugates. The conjugate of 1 plus I is 1 minus I. The conjugate of square root of 2 is negative square root of 2. So let's think about this. My degree is 4, and I've got 4 roots. So I'm all happy. See? Okay, next problem. We're given a cubic polynomial. This cubic polynomial has real coefficients. So there's real numbers in there. It says if 3 minus 2i and 5 halves are 2 roots, what's an additional root? So the key piece of information for me here is I've got a cubic. So my degree is 3, which means I'm going to have 3 total solutions. So the question is, what is my additional root? Well, if 5 halves is a root, he's not complex and he's not irrational. So he's just one of my answers. But I know here that 3 minus 2i, I know that he is a complex number. He always has to occur in pairs. So my other root is 3 plus 2i, and that is the conjugate of 3 minus 2i. And I've got 1, 2, 3 roots, and he's third degree, so I'm all set. That's it. All right, let's go on to our next problem. Could a third degree polynomial with rational coefficients have the roots 2 minus I and radical 3? Well, I know that the conjugate, sorry guys, I'm going to erase that. I know that the conjugate root theorem, I know that it tells me the conjugate root theorem says that my complex and irrational roots occur in what? Occur, O-C-C, occur in pairs. So what that means then is I'd have to have 2 more roots here. I'd have to have 2 plus I, and I'd have to have negative rad 3. So this is not a true statement. Could a third degree have these roots? No. Why? Because I'm not meeting the rule. I'm not honoring the theorem. I need to honor the conjugate root theorem. So the answer to this, guys, no. All right, next problem. We're going to use what we just learned about conjugates to actually write out an entire polynomial. So what this says is we're going to write a third degree polynomial with rational coefficients. Don't panic about that. We're going to write a third degree polynomial so we have roots at minus 4 and 2i. When we did this before, we identified our zeros, we wrote those zeros as our linear factors, and we multiplied everything out. So the first thing we have to do is identify our zeros. Our zeros happen to be negative 4, and then our 0 happens to be 2i, and then because it's a third degree, and I know that complex numbers come in pairs, I have x equals a negative 2i. And remember before what we did to turn these into linear factors is we actually worked backwards, and I got x plus 4 here. And we did this in class. So I'm going to do the same thing here. I'm going to get x minus 2I, and that's going to be, what I'm doing is going backwards and setting this equal to 0. So if I subtract 2I from each side here, what I end up getting is x minus 2I equals 0. What I got there is x minus 4 equals 0. And then if you look over here and I add 2I to each side, I end up with x plus 2I equals 0. So those are my linear factors. And then the next thing we did is we multiplied this out. So I'm going to take x plus 4 times x minus 2I times x plus 2I. And I have to multiply this whole thing out. So what I'm going to do next is the first two numbers I'm going to multiply together are these two. And there's a reason why I'm going to do that, and you will see it. So I'm just going to write down x plus 4 so I don't forget about them. And I'm going to go in and create myself a big set of brackets. And I'm going to do this multiplication. X times x gives me x squared. X times 2I gives me plus 2ix. I have minus 2I times x. That's going to give me a minus 2ix. And then I'm going to get minus 2I times plus 2I. That gives me negative 4I squared. And I know you're saying, hey, I know we have to do something with that. We do. First things first, combine like terms. A plus 2 and a minus 2 go to 0. Then the next thing I do is, here's my side work. Minus 4 times I squared is minus 4 times a negative 1, which becomes a positive 4. So now I'm left with something a lot easier to multiply. I get x plus 4 times x squared. Remember that went to 0. I simplified that to a plus 4. Now I just have to multiply these two binomials. So I end up with x cubed plus 4x. Then I come through and get plus 4x squared. And then I come through and I get plus 16. And the answer, or the directions said standard form. So x cubed plus 4x squared plus 4x plus 16. This is my polynomial. It's a third degree polynomial, and I met its conditions. It has roots at negative 4 and 2i. That's my answer. This is what I would like you to do to enter into class tomorrow. I want you to turn into me as you walk in a third degree polynomial written in standard form. So we have these roots. So you're going to start out with x equals minus 7, x equals negative 3i, and you're going to tell me x equals something else. And you will be all set. Thank you for watching. Have a good night. And I will see you guys tomorrow. Okay?